Welcome to our channel. 252 million years ago, a world alien to our own, yet the stage for one of the most fascinating chapters in our planet's history, the age of dinosaurs. From their emergence to extinction, dinosaurs dominated Earth for over 165 million years. This era saw creatures that defied imagination. The predatory Tyrannosaurus rex, the colossal Brachiosaurus, and the bizarre Therizinosaurus. Shifting continents, changing climates, and evolving ecosystems shaped the world of these prehistoric giants. Recent scientific discoveries, from feathered raptors to color-preserved fossils, continue to reshape our understanding of dinosaur life. The story of dinosaurs is one of Earth's most traumatic transformations and the relentless march of evolution. Join us as we travel to the very beginning, the start of the prehistoric era. The Earth is approximately 4.5 billion years old, a figure determined through techniques like radiometric dating of the oldest rocks and meteorites. This immense age places our planet within the early stages of the solar system, which was formed around the same time. The formation of the Earth began with a swirling cloud of gas and dust in space, known as the solar nebula. Over time, gravity pulled this material together, leading to the coalescence of particles that eventually formed the planet. Early on, the Earth experienced immense heat due to collisions with other celestial bodies, as well as the decay of radioactive elements. This intense heat caused the planet to be molten for a considerable period. As the planet cooled, a solid crust formed, allowing water vapor to condense into oceans. The development of the atmosphere also set the stage for life to emerge. This primordial environment was filled with volcanic activity and driven by enormous changes as the planet reorganized itself. An intriguing aspect of Earth's formation is the role of the moon. A widely accepted theory suggests the moon was created from debris resulting from a collision between the Earth and a Mars-sized body known as Theia. This event not only contributed to the moon's existence, but also influenced the direction of evolution on Earth, creating conditions that would ultimately support life. The Hadean Eon, spanning from the formation of the Earth to around 4 billion years ago, is characterized by extreme conditions that make it seem like a hellish environment. Named after Hades, the ancient Greek god of the underworld, this period is associated with intense geological and atmospheric activity that shaped the young planet dramatically. During the Hadean Eon, the surface of the Earth was largely molten, subjected to relentless meteorite bombardment as remnants of the solar system's formation collided with the planet. Temperatures soared and volcanic activity was rampant, releasing gases and forming a thick, toxic atmosphere. The skies would have been filled with ash and vapor, making the air unbreathable. It is a time marked by chaos and transformation, as the Earth was in a constant state of turmoil. The oceans, if they existed, were likely made of acidic and boiling water, while the likelihood of life as we know it today was virtually non-existent, with no stable surface or hospitable environment. The conditions in the Hadean Eon were far from ideal, yet this tumultuous period was crucial in laying down the foundational elements necessary for the eventual emergence of life. Despite its infernal reputation, the Hadean Eon was a phase of significant evolution. As the planet cooled and stabilized, conditions began to shift towards more suitable environments, ultimately paving the way for the next eon, the Archean, where signs of life began to appear. Thus, while the Hadean Eon epitomized extremes, it also set the stage for the vibrant world that would follow. The formation of the Earth's atmosphere and oceans was a gradual process that unfolded over millions of years, beginning in the Hadean Eon. Initially, when the planet was still molten and battered by meteorite impacts, the atmosphere primarily consisted of volcanic gases, including water vapor, carbon dioxide, hydrogen, and ammonia. As the Earth continued to cool, these gases began to accumulate, creating a thick, toxic atmosphere devoid of free oxygen. As temperatures lowered sufficiently for the outer layers of the Earth to solidify, water vapor released by volcanic eruptions started to condense into liquid form. This water began to collect, cooling, eventually forming the first oceans. Research indicates that the majority of Earth as water may have originated from volcanic outgassing and possibly from icy comets or asteroids colliding with the planet, introducing additional water. The initial oceans were vastly different from what we encounter today, filled with dissolved minerals and potentially acidic in nature. They developed in a world still experiencing significant geological activity. As the oceans formed, they began to play a crucial role in shaping the atmosphere. Over time, the interaction between water and the gases in the air facilitated the gradual formation of a more stable atmosphere. As photosynthetic organisms began to appear in the Archean eon, they released oxygen into the atmosphere through the process of photosynthesis. This introduction of oxygen dramatically changed the composition of the atmosphere, eventually leading to the development of conditions favorable for life as we understand it. Thus, the formation of the Earth's atmosphere and oceans marked the beginning of a critical evolution that would nurture diverse ecosystems throughout geological history. The Archean eon, which spanned from about 4 billion to 2.5 billion years ago, was a pivotal period in Earth's history, marked by significant geological and biological developments. One of the most remarkable events was the stabilization of the planet's crust. As temperatures dropped and geological activity began to moderate, the solid crust formed patches of land known as cratons, the ancient cores of modern continents. During the Archean, the climate was conducive to the formation of the first oceans. These bodies of water provided a unique environment where life could potentially emerge. The simplicity of life during this eon is perhaps one of its most defining features. The earliest known life forms were prokaryotic microorganisms, such as bacteria and archaea. Fossil evidence suggests that life was present as early as 3.5 billion years ago, with stromatolites layered structures created by microbial communities, serving as some of the oldest known fossils. Another significant event of the Archean eon was the emergence of photosynthesis. Some of the simple microorganisms developed the ability to harness sunlight to produce energy, a process that gradually transformed the atmosphere. This method of energy production eventually led to the release of oxygen, although it occurred on a small scale during this eon. These early organisms created a foundational shift in the chemical composition of the atmosphere, setting the stage for future biological diversification. The Archean eon was also marked by geological activity that included the formation of greenstone belts, which are regions of metamorphic rocks significant for understanding the early Earth's crust. These formations suggest that tectonic processes similar to those we observe today were occurring, hinting at the dynamic nature of the planet even in its formative years. Collectively, these events during the Archean eon laid the groundwork for more complex life forms and significant evolutionary advancements in the subsequent Proterozoic eon. The formation of the first continents, known as cratons, during the Archean eon was a gradual process influenced by numerous geological mechanisms. Initially, the Earth's crust was hot and unstable, predominantly composed of volcanic rock. Over time, as the planet cooled, tectonic processes led to the accumulation of continental crust through a combination of volcanic activity, sedimentation, and the tectonic recycling of materials. A crucial aspect of continental formation involved the emergence of island arcs and microcontinents through processes like volcanic activity and the collision of tectonic plates. These landforms gradually coalesced to create larger landmasses. The intense geological activity also contributed to the differentiation of the crust, resulting in the formation of lighter, less dense rocks, such as granite, which are primarily found in continental crust today. Evidence of these early continents comes from various geological formations and ancient rocks. One of the most significant pieces of evidence is the existence of ancient crustal remnants, often referred to as cratonic rocks, which can be found in areas known as cratons. For instance, rocks from the Acasta Gneiss in Canada and the Nouveau-Tuk Greenstone Belt, also in Canada, date back around 4 billion years and are considered some of the oldest known continental crust. Additionally, geologists utilize isotopic analysis to study ancient rocks, examining their compositions to understand their age and the processes by which they formed. The presence of banded iron formations, sedimentary deposits indicating ancient oceans, also supports a timeline for continental development and provides insights into early oceanic conditions. These geological indicators collectively paint a picture of a dynamic Earth, showing how continents gradually emerged and evolved over billions of years, setting the stage for the diverse terrestrial environments we observe today. The first single-celled organisms began to appear on Earth during the Archean Eon, a time frame from around 4 billion to about 2.5 billion years ago. The conditions on the young planet became increasingly favorable for life, as the cooling of the Earth's surface allowed for the formation of stable oceans and a solid crust. The exact process of how life originated remains a fascinating mystery, but several theories exist. One prominent idea is that simple organic molecules formed in primordial conditions, possibly aided by the energy from lightning or ultraviolet radiation. Over time, these complex molecules grew more intricate, eventually leading to the first living cells. The earliest known forms of life were prokaryotes, which lack a nucleus and are simpler in structure than more complex cells. Fossil evidence shows that these first single-celled organisms thrived in the marine environments of the Archean oceans, often in the form of microbial mats. One of the oldest and most notable fossils from this period is stromatolites. These layered structures, formed by the activity of microorganisms, provide crucial evidence of early life. Research indicates that some of these microorganisms developed the ability to perform photosynthesis, a significant evolutionary milestone. By harnessing sunlight to convert carbon dioxide and water into energy and oxygen, these creatures not only supported their own survival, but also began to alter the composition of the atmosphere. Thus, the emergence of single-celled organisms marked the beginning of a biological revolution that would ultimately transform the Earth, leading to the complex diversity of life we see today. Stromatolites are layered sedimentary structures formed by the activity of microorganisms, particularly cyanobacteria. These ancient formations emerged in shallow marine environments and serve as some of the earliest evidence of life on Earth, dating back to approximately 3.5 billion years ago during the Archean Eon. The process of stromatolite formation occurs as these microorganisms trap and bind sediments, creating distinctive mats that grow upwards over time. The importance of stromatolites in Earth's history cannot be overstated. They provide a glimpse into the early biosphere, showcasing how simple life forms interacted with their environment. As colonies of cyanobacteria thrived, they performed photosynthesis, converting sunlight into energy while releasing oxygen as a byproduct. This gradual process contributed to the oxygenation of Earth's atmosphere, setting the stage for the eventual emergence of more complex life. This phenomenon marked the beginning of the Great Oxidation Event, which occurred around 2.4 billion years ago. The rise of oxygen dramatically impacted the planet in several key ways. First, it enabled the formation of the ozone layer, a critical shield against harmful ultraviolet radiation, allowing life to venture beyond the safety of aquatic environments. Second, the increased availability of oxygen facilitated the evolution of aerobic organisms, which use oxygen to produce energy more efficiently than anaerobic processes. This advance opened up possibilities for diversification in life forms and ecological complexity. Additionally, the buildup of oxygen in the atmosphere resulted in significant geochemical changes, such as the formation of iron oxides from dissolved iron in ocean water. This led to the deposition of banded iron formations, which serve as important records of Earth's early atmospheric conditions. The changes brought about by photosynthesis not only shaped the trajectory of biological evolution, but also transformed the Earth into a more hospitable planet, ultimately allowing for the flourishing of diverse life forms. The Great Oxidation Event, occurring around 2.4 billion years ago, marked a significant turning point in Earth's history, characterized by a dramatic rise in atmospheric oxygen levels. This monumental change was largely due to the activity of photosynthetic microorganisms, especially cyanobacteria. As these organisms thrived and proliferated in the oceans, they produced substantial amounts of oxygen as a byproduct of photosynthesis, gradually transforming the composition of the atmosphere. Initially, the environment was hostile to oxygen-dependent life forms, as oxygen was highly reactive and would form compounds with other elements, such as iron. This meant that much of the newly produced oxygen was absorbed by dissolved iron in the oceans, leading to the formation of banded iron formations, evidence of an oxygen-rich atmosphere beginning to emerge. However, once the oceans became saturated with this iron, excess oxygen began to accumulate in the atmosphere, leading to a significant shift in planetary conditions. The impact of the Great Oxidation Event on life was profound and multifaceted. One of the most significant changes was the creation of an environment where aerobic organisms could thrive. These organisms use oxygen to efficiently extract energy from organic molecules, leading to the evolution of complex multicellular life. Conversely, the rise in atmospheric oxygen posed challenges for anaerobic organisms, which were adapted to low oxygen conditions. Many of these organisms faced extinction or were forced to adapt to new niches. In addition to biological changes, the Great Oxidation Event led to the formation of the ozone layer, which protects life from harmful ultraviolet radiation. This development opened up new habitats on land, allowing life to expand beyond the oceans. Overall, the Great Oxidation Event not only reshaped the atmosphere and environment of our planet, but also set the stage for the biodiversity that followed, paving the way for the evolution of plants, animals, and ultimately complex ecosystems that populate Earth today. The first multicellular organisms are believed to have evolved around 600 million to 1 billion years ago during the late Precambrian, specifically in the Ediacaran period. This marked a major evolutionary milestone, transitioning from simple single-celled life forms to more complex multicellular entities. The Ediacaran biota features some of the earliest known examples of multicellular life, showcasing a variety of forms and structures that were quite different from anything seen before. Many of the organisms from this time were soft-bodied and resembled modern jellyfish or worms, but they did not resemble any current species precisely. Fossils such as Dickinsonia and Charniodescus highlight the diversity of forms in this early group of multicellular organisms. They often exhibited simple body plans, with some displaying radial symmetry and others showing signs of bilateral symmetry, a precursor to more complex organisms. These early multicellular creatures did not have hard parts, making their fossilization relatively rare. They lived in shallow marine environments and likely relied on diffusion for nutrient absorption instead of specialized systems like those found in later organisms. The significance of this evolutionary transition lies in the cooperative arrangement of cells working together, allowing for greater complexity in structure and function. The evolution of multicellular organisms set the stage for the Cambrian explosion, a period beginning around 540 million years ago when life diversified dramatically. This event marked the rapid emergence of most major animal groups, leading to an explosion of biodiversity that still shapes ecosystems today. Thus, while these early multicellular organisms were simple by later standards, they were crucial for the development of the complex life forms that followed. The Cambrian explosion, which began around 540 million years ago and lasted for approximately 20 million years, was a pivotal period in the history of life on Earth. It witnessed an unprecedented diversification of life forms, resulting in the rapid emergence of most major groups of animals we recognize today, an event often regarded as one of the most significant moments in biological evolution. One of the key events during this time was the appearance of many phyla, a term used to classify groups of related organisms. Over a relatively short span, many complex forms of life evolved, including early ancestors of arthropods, mollusks, echinoderms, and annelids. This explosion of diversity is reflected in the fossil record, where the Burgess Shale and other sites provide rich deposits that showcase the variety of life forms that thrived during this period. Some of these organisms had hard shells, exoskeletons, or other protective structures that facilitated their fossilization, providing valuable insights into their anatomy and biology. The Cambrian explosion was also characterized by the development of complex body plans and the establishment of ecological interactions. Many organisms began to exhibit advanced features, such as eyes, specialized appendages, and more sophisticated nervous systems. This diversification led to new ecological niches, where predation and competition shaped the evolution of species. The advent of predators likely drove evolutionary adaptations in prey, resulting in an arms race that sparked further evolutionary developments. Another significant aspect of the Cambrian period was the introduction of advanced forms of mobility and habitation. Organisms such as trilobites became prominent, showcasing complex behavior and ecology. The emergence of various feeding strategies, including filter feeding and predation, contributed to the creation of complex food webs, advancing the interdependence among organisms. Overall, the Cambrian explosion not only marked a phase of unparalleled biological diversity, but also laid the foundational framework for modern ecosystems, ultimately influencing the trajectory of life on our planet for millions of years to come. The Ordovician period, which lasted from approximately 484 million to 444 million years ago, was a crucial time for the evolution of life on Earth. Following the Cambrian explosion, the Ordovician saw a further diversification of marine life, with many groups of organisms experiencing rapid evolution and expansion into new ecological niches. One of the most significant developments during the Ordovician was the evolution of a wide variety of marine invertebrates. Brachiopods continued to flourish, while the first true corals appeared, leading to the establishment of extensive coral reefs. These reefs became essential ecosystems, providing habitat for numerous organisms and significantly influencing marine biodiversity. Other notable groups that thrived included graptolites, which were colonial animals important for dating rock layers, and mollusks, which diversified into various forms, including the early cephalopods that boasted more complex structures. The Ordovician period also witnessed the emergence of early land-dwelling organisms, particularly primitive plants. Evidence suggests that simple, non-vascular plants began to colonize terrestrial environments, though life on land remained limited at this stage. This was a critical step in the transition toward a more complex terrestrial biosphere, foreshadowing the eventual terrestrial radiation of plants, insects, and other life forms in subsequent periods. As marine ecosystems became more complex, increased competition and predation drove evolutionary innovations among species. Animals developed more advanced features, such as hardened shells and robust skeletal structures, which enhanced their survival in a dynamic environment. The relationships between organisms also grew more intricate, leading to the establishment of diverse food webs, setting the stage for the major developments that would unfold in the following Silurian period. The first vertebrates to appear on Earth were jawless fish, known as agnathans, which emerged during the Cambrian period around 530 million years ago. These early vertebrates showcased the foundational characteristics of the vertebrate lineage, including a notochord, a precursor to the backbone, and a primitive nervous system. The most notable examples of these jawless vertebrates include lampreys and hagfish, which still exist today. These creatures possess elongated bodies, a cartilaginous skeleton, and a simple structure lacking true jaws. Instead of jaws, they have specialized mouthparts that allow them to attach to other organisms or feed on them, exemplifying a unique method of feeding. Their presence in ancient oceans indicates the early diversification of vertebrates in aquatic ecosystems. As the evolutionary timeline progressed into the Ordovician and Silurian periods, vertebrates began to exhibit further adaptations that allowed them to thrive. During the Silurian period, jawed fish known as gnathostans made their debut, a significant advancement that transformed vertebrate evolution. The appearance of jaws enabled these fish to exploit new feeding strategies, promoting further diversification and the establishment of complex ecosystems. The advent of vertebrates represented a major evolutionary milestone, leading to the development of more complex forms of life, including amphibians, reptiles, birds, and mammals. The lineage that began with these early jawless fish paved the way for the profound biodiversity that characterizes the vertebrate clade today. The Silurian period, spanning from approximately 444 million to 417 million years ago, marked a significant chapter in the history of life, particularly for the colonization of land by plants. During this time, the Earth experienced favorable conditions that allowed for the expansion of life from aquatic environments onto terrestrial landscapes. The earliest land plants were likely simple, non-vascular organisms closely related to modern mosses and liverworts. These pioneer plants had adapted to survive in moist environments, taking advantage of the availability of water and nutrients in the soil. One of the key adaptations that facilitated their establishment on land was the development of structures to anchor themselves in the soil, albeit rudimentary compared to the extensive root systems seen in later plants. They also evolved cuticles, which are protective layers that reduce water loss, helping them thrive in exposed terrestrial settings. The colonization of land by plants had profound ecological implications. These early plants played a critical role in the stabilization of soils, which helped to prevent erosion and created more hospitable environments for other organisms. The presence of plants also contributed to the formation of more complex ecosystems, affecting local climates and altering patterns of erosion and sedimentation. During the Silurian, the increase in terrestrial plant life likely provided new habitats and food sources for a variety of organisms. As plants began to evolve more complex structures, including vascular tissues that allowed for the efficient transport of water and nutrients, they paved the way for further diversification in the following periods. This transformation not only marked a turning point in plant evolution, but also set the stage for the emergence of terrestrial ecosystems that would support a wide array of animal life. The Devonian period, often referred to as the Age of Fishes, lasted from about 420 million to 360 million years ago. During this time, a remarkable variety of fish flourished in the oceans, establishing themselves as the dominant life forms. This period witnessed the evolution of numerous fish species, including the first appearance of both cartilaginous fishes, like sharks and rays, and bony fishes, which diversified into many different forms. Some of these fish developed notable adaptations, such as improved jaws and more complex skeletal structures, allowing them to become effective predators. While fish ruled the waters, the Devonian also saw significant developments on land. Plants began to transition from simple forms to more complex structures. Early vascular plants and the first true forests emerged, significantly altering the terrestrial landscape. These primitive plants, including species of ferns, horsetails, and the first trees like Archaeopteris, transformed not only the environment, but also the atmosphere, contributing to the increase of oxygen levels that sustained the evolutionary growth of land animals. Additionally, the Devonian period was crucial in the evolution of tetrapods, the ancestors of all land-dwelling vertebrates. Certain lobe-finned fishes began to develop adaptations for life on land, such as stronger limbs and lungs, paving the way for the transition from water to terrestrial environments. This pivotal progression marked the beginnings of amphibians, setting the stage for the eventual dominance of reptiles and mammals. The marine environment during the Devonian was also incredibly diverse, housing a plethora of invertebrate life forms. Coral reefs reached new heights, with corals and associated organisms creating complex ecosystems. The seas thrived with cephalopods, brachiopods, and trilobites, each playing critical roles in the ecological networks of their time. The Devonian period, through its diverse life forms and evolutionary advancements, laid essential groundwork for the ecosystems we recognize today. The Permian-Triassic extinction event, occurring approximately 250 million years ago, stands as the most catastrophic extinction event in Earth's history. It is estimated that up to 97% of all marine species and about 75% of terrestrial vertebrates disappeared during this event. This immense loss of biodiversity was likely triggered by a combination of factors, including intense volcanic activity, climate change, and possibly asteroid impacts. The volcanic activity in what is now Siberia released massive amounts of greenhouse gases, leading to significant temperature increases and ocean acidification. In the wake of this massive extinction, the ecological landscape underwent a remarkable transformation. With so many species gone, ecological niches were left unoccupied, creating opportunities for those organisms that survived. Among the survivors were early archosaurs and other reptiles, which were well positioned to adapt and thrive in the drastically altered environments. The extinction marked a significant turning point that allowed these early ancestors of dinosaurs to diversify and evolve over the subsequent millions of years. The Triassic period following the extinction event was characterized by an expanding array of ecosystems. Forests were repopulated with new types of plants, and importantly, reptiles started to dominate these environments. Among these reptiles were the first true dinosaurs, which began to appear in the late Triassic, showcasing a variety of forms and sizes. With the competition for resources diminished and various ecological niches available, dinosaurs experienced rapid evolution, leading to their eventual rise as dominant terrestrial vertebrates throughout the Mesozoic era. This transition illustrates how extinction events, while catastrophic, play crucial roles in shaping the course of evolution. The Permian-Triassic extinction, despite the devastating loss of life, cleared the way for new life forms to emerge, setting the stage for the age of dinosaurs, which would rule for over 160 million years. The history of life on Earth is profoundly influenced by such events, showing the intricate balance of ecosystems, resilience of life, and ongoing evolution in response to change. The first dinosaurs emerged during the late Triassic period, approximately 230 million years ago. These early dinosaurs were generally small and bipedal, with many resembling modern-day birds in certain ways. They had slender bodies and long tails, which helped with balance and agility. Among the earliest known dinosaurs are species like Eiraptor and Herrerasaurus, both of which were relatively lightweight and nimble, roughly the size of a dog. In terms of appearance, the first dinosaurs had features that reflect their evolutionary adaptations. They possessed sharp teeth that would have been effective for a diet of meat for the carnivorous species, whereas herbivorous dinosaurs developed flat, grinding teeth suited for eating plants. Their limbs were positioned directly beneath their bodies, a key trait that distinguished them from many of their contemporary reptilian relatives, allowing for more efficient movement and supporting larger body sizes in their descendants. Despite their relatively modest stature compared to later giants, these early dinosaurs exhibited a variety of forms and adaptations. Some were agile hunters, while others grazed on the lush vegetation that was proliferating after the Permian-Triassic extinction. The diversity in their body shapes and sizes laid the groundwork for the various dinosaur lineages that would evolve in the Jurassic and Cretaceous periods, leading to the iconic giant species we often think of today. As they adapted to different environments and ecological niches, the characteristics of these early dinosaurs set the stage for future diversification. This early phase of dinosaur evolution was crucial, signaling the beginning of a lineage that would dominate the terrestrial ecosystems for millions of years to come, evolving into enormous creatures and complex species that would capture the imagination of generations. Dinosaurs evolved from a group of reptiles known as archosaurs, which also includes crocodiles and birds. This evolutionary journey began during the late Triassic period, when significant environmental and ecological changes presented new opportunities for survival and adaptation. The early archosaurs were characterized by their distinct skull structure and limb posture, traits that would ultimately influence the development of dinosaurs. Initially, the early archosaurs diversified into two main lineages: the Pseudosuchia, which led to modern crocodiles, and the Avamtautosalia, which paved the way for dinosaurs and their close relatives. One of the critical adaptations that distinguished the ancestors of dinosaurs was the arrangement of their limbs. These ancestors developed an upright posture with legs positioned directly beneath their bodies, allowing for more efficient locomotion and greater speed. This adaptation was crucial for their survival in changing environments. As archosaurs continued to evolve, various traits began to emerge that would define the future dinosaurs. For instance, changes in skull shape and the development of diagnostic features, such as new types of teeth and more sophisticated respiratory systems, provided advantages in feeding and metabolism. Some small, agile archosaurs began to exhibit characteristics associated with bipedal locomotion, enabling them to run faster and escape predators or hunt for food. Throughout the Triassic period, a gradual process of natural selection favored certain traits in these early archosaurs. Larger body sizes, increased agility, and adaptations for a variety of diets allowed various groups to thrive. By the late Triassic, these developments culminated in the first true dinosaurs, who gradually filled the ecological niches left vacant after previous extinction events. This evolution exemplifies how small adaptations over time can lead to significant changes, shaping the trajectory of life on Earth and leading to one of the most successful and diverse groups of animals in history. Dinosaurs, a diverse and remarkable group of reptiles, are defined by several key characteristics that set them apart from other reptiles. One of the most significant traits is their distinctive hip structure. Dinosaurs possess an upright posture, with their legs positioned directly beneath their bodies, rather than splayed out to the sides, as seen in most other reptiles. This anatomy allowed for more efficient locomotion and greater stamina, enabling them to thrive in various environments. Another defining feature of dinosaurs lies in their unique teeth and jaw structures. Different groups of dinosaurs adapted their teeth to suit their diets, whether they were herbivorous, carnivorous, or omnivorous. Herbivorous dinosaurs often exhibited flat, grinding teeth suited for processing plant material, while carnivorous species had sharper, serrated teeth designed for slicing through flesh. This diversity in dentition reflects the varied ecological niches dinosaurs occupied. Dinosaurs also exhibited variations in their skeletal structures, particularly in their limbs and tails. Many had long, flexible tails, which not only provided balance, but also served various functions, such as communication or defense against predators. The forelimbs of some dinosaur species evolved into specialized forms, adapting for flight, grasping, or other functional roles within their respective environments. Lastly, dinosaurs possessed distinct reproductive traits. They laid eggs and exhibited nesting behaviors that allowed for the protection and care of their young. The combination of these characteristics, upright posture, specialized teeth, varied skeletal structures, and reproductive strategies, established dinosaurs as a unique and successful group of animals. This adaptability contributed to their dominance on land for over 160 million years, showcasing the incredible evolutionary success of these ancient creatures. The climate and geography of the Triassic period played significant roles in shaping the evolution of dinosaurs. During this time, the Earth was characterized by a primarily arid climate, with vast deserts and limited rainfall in many regions. This environment led to the proliferation of drought-resistant vegetation, such as cycads and ginkgos, which provided essential food sources for the early herbivorous dinosaurs. The challenging conditions also favored adaptability, as species that could thrive in the fluctuating climates gained a competitive edge. Geographically, the Triassic period was marked by the presence of the supercontinent Pangaea, which had a profound impact on animal evolution. The unification of landmasses allowed for the dispersal of species across vast distances, promoting genetic exchange and diversity. However, it also meant that many areas were isolated from one another, leading to unique evolutionary paths in different regions. This vast expanse of land provided numerous ecological niches, allowing early dinosaur ancestors to adapt to varying climates and environments, from hot deserts to more temperate areas. As Pangaea began to break apart toward the end of the Triassic, it created new coastlines and inland seas, further diversifying habitats. This geological change introduced new ecological opportunities and challenges, encouraging dinosaurs to explore different survival strategies. Species that could adapt to fragmented landscapes were likely to flourish, leading to the emergence of various dinosaur lineages. Moreover, the Triassic climate, with its fluctuating temperatures and precipitation patterns, drove rapid evolutionary changes. Dinosaurs that could cope with changing environmental conditions had a better chance of survival and reproduction. The interaction between climate, geography, and the evolutionary paths of early dinosaurs facilitated adaptations that would ultimately lead to their dominance in subsequent periods, setting the stage for the Mesozoic era's rich diversity of dinosaur species. Dinosaurs are primarily classified into two main groups, the Saurischia and the Ornithischia. This classification is based on their hip structures and other anatomical features. Relationships are often determined using phylogenetic analysis to understand these connections. Paleontologists examine fossilized remains, studying skeletal features, teeth, and other anatomical parts to categorize dinosaurs into different clades, which represent evolutionary branches. The use of cladistics allows scientists to determine how dinosaurs are related to one another and to track their evolution over time. Additionally, within these main groups, dinosaurs are further classified into various families and species based on specific traits and fossil evidence. This system of classification not only helps organize the vast diversity of dinosaurs, but also enhances our understanding of their evolutionary history, adaptations, and interactions within their ecosystems. By studying these relationships, scientists can trace the intricate evolution of dinosaurs and the ecological roles they played. Throughout the Mesozoic era, herbivorous and carnivorous dinosaurs exhibited significant differences in both anatomy and behavior, reflecting their adaptations to these distinct diets. One of the most notable anatomical variations lies in their teeth and jaw structures. Herbivorous dinosaurs, such as Triceratops and Brachiosaurus, typically possessed flat, broad teeth designed for grinding and chewing tough plant material. Their jaws were often structured for lateral movement, allowing them to effectively process vegetation. In contrast, carnivorous dinosaurs like Tyrannosaurus rex and Velociraptor had sharp, serrated teeth suitable for slicing through flesh, and their jaws often featured a more forward motion conducive to capturing and holding on to prey. The body structures of these two groups also differed remarkably. Herbivorous dinosaurs often had larger, bulkier bodies supported by strong limbs to bear their weight and facilitate movement across diverse landforms. Many of them exhibited long necks, allowing them to reach high vegetation in trees or graze over extensive areas of ground cover. In contrast, Many carnivorous dinosaurs were built for speed and agility, with lighter, more streamlined bodies and longer limbs designed for quick bursts of movement. Theropods, the group containing most carnivorous dinosaurs, often had powerful hind limbs for running and well-developed forelimbs for grasping or attacking. Behaviorally, these anatomical adaptations influenced feeding strategies and social interactions. Herbivorous dinosaurs tended to form herds for protection against predators, utilizing their size and numbers to deter attacks. Their grazing habits often led them to migrate seasonally, seeking out abundant food sources. In some species, especially in later periods, elaborate nesting behaviors were observed, indicating parental care for their young. Carnivorous dinosaurs, on the other hand, developed various hunting strategies. Some were solitary predators, while others, like the pack-hunting theropods, exhibited cooperative behaviors to tackle larger prey. Their predatory nature required keen senses for detecting movement and tracking down animals, resulting in adaptations like sharp eyesight and acute hearing. The contrasting anatomical traits and behavioral patterns highlight the diverse ecological niches that herbivorous and carnivorous dinosaurs occupied, shaping the interactions within their ecosystems and influencing the evolutionary paths of both groups. Some of the largest dinosaurs to ever live include Argentinosaurus, Brachiosaurus, and Spinosaurus. Argentinosaurus is often considered one of the biggest, reaching lengths of approximately 100 feet or more and weighing up to 100 tons. Brachiosaurus, known for its long neck and towering stature, could grow similarly large, particularly in its ability to reach high vegetation. Spinosaurus, while not as long as some sauropods, was notably massive and unique, with estimates suggesting it could grow over 50 feet long and weigh around 8 tons, distinguished by its sail-like spine. These colossal sizes resulted from various growth strategies and evolutionary adaptations. In comparison to smaller dinosaurs, larger species enjoyed significant advantages, including increased access to food resources. As herbivores, for example, gigantic dinosaurs could reach high into trees for leaves, consuming vast amounts of vegetation that smaller animals could not, thereby reducing competition for food. Additionally, larger body sizes provided better protection against predators, allowing the largest dinosaurs to thrive in their environments without as many natural threats. The growth of these dinosaurs was also influenced by their efficient respiratory and metabolic systems. Many of the largest dinosaurs were thought to have had air sacs, like modern birds, which may have allowed for more efficient nutrient absorption and oxygen intake. This adaptation would enable them to maintain their immense size while optimizing their energy usage. Furthermore, their rapid growth during early life stages would have been key, as these animals could quickly achieve sizes that offered advantages in survival and reproduction. The combination of optimal feeding strategies, effective adaptation mechanisms, and evolutionary advantages allowed these massive dinosaurs to not only grow to such significant sizes, but also to dominate their ecosystems for millions of years. The environmental conditions of the Mesozoic era likely played a role in facilitating the development and reign of these extraordinary giants, which captured the imagination of scientists and the public alike. Several dinosaurs are well known for their unusual features and adaptations, showcasing the incredible diversity within this group. One striking example is the Stegosaurus, recognized for its distinctive backplates and spiked tail, known as a thagomizer. The large, bony plates along its back were likely used for display, thermoregulation, or defense against predators, while the tail spikes served as a formidable weapon. These adaptations made Stegosaurus stand out among herbivorous dinosaurs. Another unique dinosaur, the Rhesunosaurus, is characterized by its extremely long claws, which could reach lengths of over a foot. These claws, unlike typical carnivorous dinosaur features, suggest a primarily herbivorous diet, likely used for foraging vegetation. Its unusual body proportions, with a bulky torso and long, slender limbs, reveal that adaptations can lead to unexpected feeding strategies. Pachycephalosaurus offers yet another example of unusual adaptations, known for its thick dome-shaped skull, which could reach up to 10 inches in thickness. This dome may have been used in head-butting behaviors, similar to those seen in modern rams, providing a competitive edge in male-to-male interactions. The unique adaptations of these dinosaurs illustrate not only the variability within the dinosaur clade, but also how specific traits evolved to meet the challenges of their environments and enhance survival strategies. These remarkable adaptations contribute to our understanding of how dinosaurs interacted with each other and their ecosystems, further highlighting their fascinating history. Dinosaurs exhibited a remarkable range in size, from some of the smallest known species to the enormous giants that roamed the earth. On the smaller end of the spectrum, species like Microraptor were about the size of a crow, with an estimated length of around 2 feet. Microraptor was a feathered dinosaur, showcasing adaptations that allowed it to glide between trees, highlighting how even small dinosaurs could develop specialized features for survival. Conversely, at the opposite end of the scale, massive dinosaurs like Argentinosaurus and Brachiosaurus achieved titanic sizes. Argentinosaurus is often considered one of the largest land animals ever to exist, reaching over 100 feet in length and weighing upwards of 100 tons. Brachiosaurus, distinguished by its long neck and large body, also grew to similar proportions, towering above the vegetation to reach leaves high in the trees. These enormous sizes were advantageous for foraging and evading predators, as larger animals often face fewer threats than their smaller counterparts. The variations in size among dinosaurs were facilitated by a combination of evolutionary pressures, ecological niches, and available resources. Larger herbivorous dinosaurs could efficiently exploit abundant plant material, allowing them to grow substantially as they matured. Moreover, their sheer size helped them deter potential predators. Meanwhile, smaller dinosaurs often occupied different ecological roles, such as those who thrived as agile hunters or those adapted for tree-dwelling lifestyles, using their size for speed and agility rather than sheer strength. These size variations illuminate the vast diversity of dinosaurs and their ability to adapt to different environmental conditions. They also illustrate how dinosaurs, regardless of size, played critical roles within their ecosystems, contributing to complex food webs and interactions that shaped the Mesozoic era. The differences in size, from the diminutive to the gargantuan, underscore the incredible evolutionary journey that these ancient creatures underwent, ultimately leading to their success and dominance on Earth for millions of years. Tyrannosaurus rex is often regarded as one of the most formidable predators in the history of dinosaurs, and several key features contributed to its reputation. One of the most striking characteristics of the T-Rex was its size, standing up to 40 feet long and weighing around 9 tons. Its sheer mass alone made it an imposing figure in its ecosystem. Its powerful legs allowed for quick bursts of speed, enabling it to chase down or ambush prey effectively, despite its large size. The anatomy of Tyrannosaurus rex also played a crucial role in its predatory success. Its skull was massive, housing a set of sharp, serrated teeth that could exceed 12 inches in length. These teeth were specifically adapted for biting through the flesh and bone of its prey, delivering immense crushing power. Additionally, T-Rex had formidable jaw muscles that provided a powerful bite force, estimated to be one of the strongest among terrestrial animals. This strength allowed it to take down large herbivorous dinosaurs, such as Triceratops and Hadrosaurus. Tyrannosaurus rex also possessed keen sensory capabilities, particularly excellent vision and a strong sense of smell. Research suggests that its eyesight was binocular, providing depth perception essential for hunting. Its olfactory bulbs were large, indicating a well-developed sense of smell that would have allowed it to track down prey from significant distances. The variations in size, shape, and ornamentation of these structures provide important insights into their functional significance. One of the primary purposes of head crests and frills was likely related to display and communication among individuals. The elaborate structures could have served as visual signals to attract mates or assert dominance within social groups. Brightly colored crests or intricate frills may have enhanced visibility, allowing individuals to signal their fitness and health to potential partners. In species that lived in herds, such features could have also played a role in social interactions, helping to establish hierarchy and cohesion within the group. In addition to social signaling, head crests and frills might have offered some defensive advantages. For example, specific features could have provided a protective barrier against predatory attacks, shielding vital areas such as the neck and head. By presenting these intimidating structures to threats, dinosaurs like Triceratops could appear larger and more formidable, potentially deterring predators. Additionally, the presence of horns or sharp edges on frills might have been used in physical confrontations with rivals during mating contests or territory disputes. Lastly, some researchers suggest that crests and frills may have played a role in thermoregulation. The large surface area of these structures could have helped dissipate heat, allowing dinosaurs to regulate their body temperature more efficiently in certain climates. This adaptation would have been particularly beneficial in warmer environments, giving them a physiological advantage as they engaged in activities such as foraging or displaying behaviors. Overall, the evolution of head crests and frills highlights the complexity of dinosaur behavior and adaptation. By serving functions related to communication, defense, and thermoregulation, these features contributed significantly to the survival and success of various dinosaur species in the diverse ecosystems of the Mesozoic era. Dinosaur armor and spikes were highly effective adaptations that served as important defensive mechanisms against predators. These physical features evolved in various species, particularly in dinosaurs like Ankylosaurus and Stegosaurs. The presence of bony plates, spikes, and armored skin provided multiple layers of protection, enhancing their chances of survival in a world filled with formidable predators. Armored dinosaurs like Ankylosaurus showcased a body covered with thick, bony scutes. These plates acted like a shell, providing a tough exterior that could absorb and deflect attacks from predators. The compactness and rigidity of this armor not only made it difficult for carnivores to inflict damage, but also helped protect vital organs and tissues. In addition to their tough exterior, many armored dinosaurs had tails equipped with club-like structures or spikes. These powerful tails could be swung with significant force, allowing the dinosaurs to fend off attackers effectively. The ability to deliver a strong defensive blow significantly increased their survivability during predator encounters. Spikes and other defensive structures also contributed to intimidation as a form of passive defense. Dinosaurs, such as Stegosaurus, featured prominent spikes along their backs, making them less appealing targets for predators. The sight of such formidable defensive adaptations could deter some carnivores from attacking. By presenting these threatening spikes or armoring in encounters, these dinosaurs could potentially avoid confrontation altogether, sparing themselves from the risks associated with an attack. It is essential to consider the ecological context when evaluating the effectiveness of armor and spikes. While these adaptations provided substantial protection, they were not foolproof. Some predatory dinosaurs likely evolved strategies to circumvent these defenses, such as targeting weaker points or employing pack hunting tactics. Nonetheless, the combination of physical armor, spikes, and potential defensive behaviors made these adaptations incredibly effective in offering a degree of safety to armored dinosaurs, allowing them to thrive amidst the challenges posed by their predators. Fossil records provide fascinating insights into the defensive behaviors of ancient organisms. One of the most compelling pieces of evidence comes from the physical characteristics of prehistoric animals and plants. For example, many species developed protective features such as thick shells, spines, or armored plating. The presence of these traits suggests that they evolved as defenses against predators. The distinctive characteristics, like the horns on ceratopsians or the encased bodies of trilobites, indicate that these organisms faced significant predation pressures. Additionally, trace fossils offer crucial insights into these defensive behaviors. Fossilized footprints or burrows can signify that animals were attempting to escape from threats or were hiding from potential predators. For instance, certain fossilized burrows show signs of being constructed more robustly or in a way that would allow easier access to fleeing, but also provide protection against threats. These behaviors demonstrate not just the act of fleeing, but an intelligent design in their habitat that indicates a need to defend against predators that were present at that time. Paleoecological studies also play an essential role in understanding defensive behavior. By examining the assemblage of fossilized remains found in certain strata, paleontologists can deduce predator-prey dynamics. A large presence of predatory species, along with the remains of herbivorous species, may suggest that those herbivores were actively developing defenses. Evidence of bite marks on fossils can indicate interactions that led to the evolution of protective traits. Furthermore, some fossils include evidence of communal defense strategies. For example, groups of certain species are found fossilized together, exhibiting a potential strategy to fend off predators through numbers. This communal behavior stands as a testament to how social structures might have evolved as a defense mechanism. Such evidence illustrates that even in the ancient world, organisms were not solely passive victims. They actively adapted and developed strategies for survival. Dinosaurs showcased remarkable adaptability to their ever-changing environments over millions of years, a trait that played a crucial role in their survival through diverse conditions. As temperatures fluctuated, ecosystems shifted, and food sources became scarce, dinosaurs evolved in various ways to cope with these challenges. For instance, changes in climate and vegetation led to alterations in their diets. Some herbivorous dinosaurs developed elongated necks to reach higher foliage, allowing them to exploit available plant resources efficiently. This adaptation highlights not just survival instinct, but also a remarkable evolution of both morphology and behavior in response to environmental pressures. Additionally, the diversity of dinosaur species during the Mesozoic era shows how variations in physical characteristics enabled different groups to thrive in distinct habitats. For instance, large sauropods roamed the open plains, while smaller theropods adapted to more complex forested environments. The morphological differences among these species reveal their responses to habitat availability and competition, illustrating the dynamic nature of evolutionary adaptations. This diversification was crucial for the dinosaurs, allowing them to occupy a wide range of ecological niches. Furthermore, the fossil record provides evidence of behavioral adaptations in response to environmental changes. For example, some dinosaurs exhibited migratory patterns similar to modern birds or mammals, moving to areas with more favorable climates or abundant food sources. The ability to migrate in search of energy-rich resources helped them cope with seasonal changes and habitat variability. Such behavioral strategies reflect the evolutionary pressures they faced and the necessity of adapting for survival in fluctuating ecosystems. Another significant factor was the impact of extinction events, which provided opportunities for dinosaurs to occupy newly available niches. After the Permian extinction, dinosaurs surged in diversity, filling the gaps left by extinct species. This has been a recurring theme in their evolutionary history, where catastrophic events led to rapid adaptations and the emergence of new species better suited to the new conditions. Through a combination of physical adaptations, behavioral changes, and the ability to exploit different environmental opportunities, dinosaurs thrived and diversified, leaving a lasting legacy in the fossil record. Dinosaur lineages experienced several major evolutionary transitions that significantly shaped their development and diversity over time. One of the most prominent transitions was the shift from bipedal to quadrupedal locomotion. Early dinosaurs were predominantly bipedal, like the small theropods. Over millions of years, some theropod lineages, including the iconic sauropods, transitioned to a quadrupedal stance. This shift allowed these massive animals to support their significant body sizes efficiently, giving rise to some of the largest land animals in history. Another critical transition occurred in the evolution of feathers. Initially present in small theropods, the development of feathers was a significant evolutionary milestone, linking dinosaurs to modern birds. Initially, feathers may have served functions such as insulation, display, or even gliding before their role in flight became evident. This transition illustrates not only adaptation for survival, but also the complex relationships and evolutionary pathways connecting dinosaurs to their avian descendants. The emergence of various feeding strategies represents another major transition. Dinosaurs diversified into numerous dietary niches, with some evolving into specialized herbivores or carnivores. For example, the development of specialized teeth in Hadrosaurus for grinding plant material, and the sharp, serrated teeth of theropods for slicing through flesh highlight how different lineages adapted to exploit available resources effectively. These adaptations reflect the ecosystem's diversity and the competition among species, showcasing the dynamic nature of evolutionary change within these lineages. Finally, the transition from non-avian dinosaurs to birds marks one of the most fascinating evolutionary changes. The late Jurassic and early Cretaceous periods witnessed the evolution of smaller theropods with features conducive to flight, such as lightweight skeletons, advanced respiratory systems, and refined wing structures. This crucial transition not only showcases the adaptability of dinosaur lineages, but also emphasizes the resilience of life, leading to the modern birds we see today, directly descended from theropod dinosaurs. Each of these transitions highlights the innovative and diverse ways in which dinosaurs adapted to their environments over millions of years, shaping the evolutionary landscape we study today. The evolution of flight in dinosaurs is a remarkable story of adaptation and innovation within prehistoric life. It is widely believed that flight originated in small theropods, a group of bipedal dinosaurs that included species like Velociraptor and Archaeopteryx. Key to this evolutionary transition was the development of features that facilitated aerial movement. Initially, feathered limbs likely provided insulation or display functions. Over time, these structures became adapted for gliding, leading to the first rudimentary forms of flight. One prevailing theory suggests that the ancestors of birds may have used their feathers for climbing through trees, gaining access to food sources, and escaping predators. This behavior, often referred to as the arboreal hypothesis, indicates that the early stages of flight were not purely for propulsion, but served multiple survival functions. The evolution of feathers became crucial during this period, providing not just aerodynamic benefits, but also enhancing balance and maneuverability as these small dinosaurs navigated their environments. In addition to feather evolution, changes in body structure were significant in the transition to flight. Certain theropods underwent modifications in their skeletal systems, including lightweight bone structures, which helped reduce body mass. Their forelimbs began to evolve into wing-like appendages, allowing for more effective flapping and manipulation of airflow. As these adaptations occurred, some theropods developed increased breast muscles to power their wings, further enhancing their flying capabilities. This adaptation illustrates the intricate link between anatomical changes and the demands of a new mode of locomotion. The first birds, emerging during the late Jurassic period, represent the culmination of these evolutionary processes. Archaeopteryx, often cited as the earliest known bird, exhibited both dinosaur and avian traits, such as feathers, a wishbone, and even teeth, showcasing this transitional phase. The evolution of flight is therefore not seen as a single event, but as a series of gradual adaptations that transformed small, feathered theropods into the birds we recognize today. This incredible journey exemplifies how environmental pressures and biological innovations can drive significant evolutionary change, resulting in the diverse avian life we witness across the globe. Convergent evolution among dinosaur species is a fascinating phenomenon where unrelated lineages develop similar traits in response to comparable environmental pressures or challenges. One prominent example can be seen with the development of herbivorous adaptations among different dinosaur groups. Both hadrosaurs, known as duck-billed dinosaurs, and sauropods, the long-necked giants, evolved specialized teeth and jaw structures for processing plant material, despite being distantly related. These adaptations illustrate how similar dietary needs can drive the emergence of comparable physical traits. Another striking case of convergent evolution is found in the armor that developed in different dinosaur lineages. Stegosaurs and ankylosaurs, for instance, both formed protective armor, but did so independently. Stegosaurs, characterized by their distinctive plates and spikes along their backs, and ankylosaurs, known for their heavily armored bodies and club-like tails, adapted to their respective environments to deter predators. This convergence highlights how similar defensive strategies can evolve in response to predation pressures, leading to analogous anatomical features in species with entirely different evolutionary histories. The development of flight is also an example of convergent evolution, with various theropod dinosaurs showing adaptations for gliding or flying. While the lineage leading to modern birds adapted feathers for flight, other theropods, such as certain species of dromaeosaurs, developed wings independently. These adaptations enabled both groups to exploit aerial niches, showcasing how different taxa can evolve similar traits to address the same ecological challenges, despite their separate evolutionary paths. Additionally, the development of body plans suited to different environments underscores the role of convergent evolution in dinosaurs. For instance, some small theropods evolved a cursorial body structure, optimizing them for speed and agility in open environments. Conversely, large predatory dinosaurs, like Allosaurus and Carcharodontosaurus, displayed similar adaptations, despite originating from different lineages. These evolutionary parallels reflect the powerful influence of environmental selection pressures in shaping physical characteristics across unrelated species. Convergent evolution among dinosaurs illustrates how nature often finds similar solutions to similar problems, resulting in diverse yet analogous adaptations throughout the ages. Dinosaurs and mammals coexisted for a significant span of time, particularly during the Mesozoic era, which lasted for about 180 million years. While dinosaurs dominated terrestrial ecosystems, small mammals were often present as inconspicuous creatures, adapting to life in their shadows. Early mammals tended to be small, nocturnal, and likely insectivorous, which allowed them to thrive in niche environments that dinosaurs did not exploit. This size and lifestyle minimized competition with dinosaurs and offered mammals a degree of safety from predation. As dinosaurs flourished, mammalian evolution began to take shape through various adaptations. Fossil evidence indicates that mammals developed important traits that helped them survive in a world dominated by larger reptiles. For example, mammals had more advanced ear structures and a differentiated set of teeth, which allowed them to exploit a wider range of food sources. These features contributed to their resilience and adaptability, traits that would be vital as the environment changed throughout the Mesozoic. Mammals were often small and lived in burrows or trees, taking advantage of arboreal habitats. This adaptation not only provided safety from larger predators, but also opened up access to different food sources. Interestingly, some mammals developed similar traits to their dinosaur counterparts, illustrating convergent evolution. For instance, the presence of gliding mammals during this era shows how different lineages can evolve similar adaptations based on their environmental needs. The coexistence of dinosaurs and mammals shifted dramatically during the Cretaceous-Paleogene extinction event, approximately 66 million years ago. This mass extinction wiped out nearly 75% of Earth's species, including the non-avian dinosaurs. In the aftermath, mammals seized the opportunity to diversify and evolve rapidly, entering niches left vacant by their dinosaur competitors. This led to the gradual emergence of larger mammals, ultimately leading to the rich diversity of mammalian life we observe today. The evolutionary history of dinosaurs and mammals thus reflects a complex interplay of survival, adaptation, and change, showcasing how life continues to evolve in response to environmental shifts. The Cretaceous-Paleogene extinction event, occurring around 66 million years ago, stands as one of the most significant mass extinctions in Earth's history. This event marked the boundary between the Cretaceous period, known for the dominance of dinosaurs, and the Paleogene period, which saw the rise of mammals. It resulted in the extinction of approximately 75% of all species on the planet, including the non-avian dinosaurs, marine reptiles, and many plant species. The unfolding of this dramatic extinction event is often attributed to a combination of catastrophic causes, but the most popular theory centers around a massive asteroid impact. Evidence for this theory includes the discovery of a layer of iridium-rich clay at the Cretaceous-Paleogene boundary, found in various locations worldwide. Iridium is rare on Earth's surface, but common in asteroids, suggesting that a cosmic collision had significant geological consequences. This impact is believed to have created the Chicxulub crater, located on the Yucatan Peninsula in Mexico, with an estimated diameter of over 180 kilometers. The aftermath of the impact triggered a series of environmental upheavals. The collision would have released vast amounts of energy, resulting in wildfires, tsunamis, and a nuclear winter scenario, where dust and debris blocked sunlight, leading to a dramatic drop in temperatures. This sudden change in climate would have disrupted photosynthesis, causing a collapse of food chains both on land and in the oceans. As a result, many plant species became extinct, significantly affecting herbivorous dinosaurs and those that relied on them for sustenance. While the asteroid impact is the most widely acknowledged cause, other factors likely contributed to the extinction event. Extensive volcanic activity, particularly in the Deccan Traps region of present-day India, released large volumes of volcanic gases, including carbon dioxide and sulfur dioxide. This could have caused long-term climatic shifts and acid rain, further destabilizing the environment. Together, these catastrophic events dramatically altered ecosystems and paved the way for the mammals and other surviving species to flourish in the subsequent Paleogene period. The Cretaceous-Paleogene extinction event marked a pivotal moment in Earth's history, reshaping the course of evolution and leading to the rise of mammals as the dominant terrestrial vertebrates. The asteroid impact theory for dinosaur extinction is substantiated by several lines of compelling evidence that collectively paint a vivid picture of this catastrophic event. One of the most notable pieces of evidence is the discovery of a thin layer of iridium-rich clay at the Cretaceous-Paleogene boundary, found in various locations around the globe. Iridium is a rare metal on Earth's surface, but is typically abundant in asteroids, and its presence in this layer suggests that an extraterrestrial object struck Earth at this time. The widespread distribution of this iridium anomaly supports the idea that a significant impact event took place. In addition to the iridium layer, the Chicxulub crater in Mexico serves as a critical source of evidence. This massive impact structure measures over 180 kilometers in diameter and dates to approximately the same period as the extinction event. Geophysical surveys and geological studies of the region indicate that the impact was powerful, enough to have caused catastrophic environmental changes. The crater provides insights into the energy released during the collision, supporting the hypothesis that it triggered global consequences. Further supporting the asteroid impact theory are the findings of shocked quartz and microtectites within the same boundary layer. Shocked quartz forms under extreme pressure and temperature conditions, typical of high-energy impacts, indicating that a significant force was exerted upon the Earth's surface. Microtectites, tiny glassy beads formed from molten material ejected during an impact, provide additional evidence of the explosive nature of the event. Collectively, these findings point to the physical effects of an asteroid collision. Lastly, the coinciding timing of the impact event and the mass extinction observed in the fossil record reinforces the notion that the two are linked. The abrupt transition seen in fossil assemblages, with a significant loss of biodiversity following the boundary layer, aligns with the catastrophic consequences presumed to arise from the impact. This aligned evidence of Iridium the Chicxulub crater shocked minerals, and the subsequent ecological disruption presents a well-rounded case for the asteroid impact theory as a principal factor in the extinction of the non-avian dinosaurs and many other species during this pivotal period in Earth's history. While the asteroid impact theory is the most prominent explanation for the extinction of the dinosaurs, other factors likely contributed to the demise of these magnificent creatures. One significant factor is volcanic activity, particularly related to the extensive volcanic eruptions that formed the Deccan Traps in what is now India. These eruptions occurred around the same time as the asteroid impact and released vast amounts of volcanic gases, including carbon dioxide and sulfur dioxide. The resulting climatic effects caused by these gases could have led to global cooling and acid rain, severely disrupting Earth's ecosystems. The volcanic activity would have contributed to significant shifts in climate by increasing atmospheric dust and aerosols, which could block sunlight, further inhibiting photosynthesis. This would stress plant communities, consequently affecting herbivorous dinosaurs that depended on these plants for food. The combination of volcanic eruptions and the asteroid impact could have created a hostile environment that made survival challenging for many species. Additionally, changes in sea levels and ocean chemistry during the late Cretaceous period played a role in the overall ecosystem disruptions. Fluctuations in sea levels can lead to habitat loss for many marine and terrestrial species. Ocean acidification, due to increased carbon dioxide levels, may have affected marine life, including the organisms at the base of the food web. The decline of these marine environments would have ripple effects on terrestrial ecosystems, further stressing existing species. Another factor to consider is the ecological competition and evolutionary pressures that existed prior to the extinction event. Dinosaurs had already faced various competition challenges towards the end of the Cretaceous, and as environments changed, the struggle for resources would have intensified. This background pressure could have made them more susceptible to catastrophic events like the asteroid impact and volcanic activity. Overall, the extinction of the non-avian dinosaurs was likely a result of a complex interplay of catastrophic events and gradual ecological changes rather than a single cause. Each factor contributed to an increasingly hostile environment, ultimately leading to the dramatic loss of biodiversity that transpired at the end of the Cretaceous period. Several groups of animals successfully survived the mass extinction at the end of the Cretaceous period, and their ability to endure came down to a combination of advantageous traits and ecological resilience. One of the most notable survivors was the group we now know as mammals. These small, nocturnal creatures had already established a diverse array of adaptations that allowed them to exploit various niches. Their small size offered a significant advantage in the rapidly changing environments following the extinction, providing them the ability to hide from predators and access resources that larger animals could not. Birds, which are considered the direct descendants of theropod dinosaurs, also managed to survive the extinction event. The presence of feathers, coupled with the ability to fly, likely provided these avian species with the means to escape unfavorable conditions or access food sources that were less affected by environmental turmoil. This adaptability allowed birds to thrive in the aftermath of the extinction filling ecological niches left vacant by the demise of larger dinosaurs. Another group that weathered the extinction was the reptiles, particularly some lineages of lizards and turtles. These reptiles often possess traits such as low metabolic rates and the ability to enter states of dormancy, which makes them better equipped to cope with drastic environmental changes. Their versatile diets also allowed them to adapt to varying food availability, giving them an edge in survival during this tumultuous time. Lastly, amphibians, including frogs and salamanders, also managed to survive the mass extinction. Their life cycles often involve both land and aquatic environments, enabling them to exploit diverse habitats. Amphibians' permeable skin and ability to withstand different environmental conditions provided resilience against the dramatic changes that followed the extinction event. The ability of mammals, birds, certain reptiles, and amphibians to survive the mass extinction stemmed from their small size, adaptability to changing environments, varied diets, and ecological strategies that allowed them to navigate the challenges posed by a world undergoing profound transformation. These survivors laid the groundwork for the eventual diversification of life in the post-Cretaceous landscape. The extinction at the end of the Cretaceous period is believed to have occurred relatively rapidly, likely over a span of just a few thousand to several 100,000 years. While some aspects of the longer-term ecological changes may have unfolded over millions of years, the immediate effects of the catastrophic events that triggered the extinction, particularly the asteroid impact, would have been felt almost instantaneously. The initial impact would have caused fires, tsunamis, and a tremendous release of energy, leading to an immediate and catastrophic alteration of the environment. The immediate effects included a dramatic drop in temperatures due to debris, and dust ejected into the atmosphere, which blocked sunlight and led to what is often referred to as an impact winter. This phenomenon severely disrupted photosynthesis and caused widespread destruction of plant life. As plants perished, herbivorous dinosaurs found themselves facing food shortages, leading to cascading effects throughout the food web. The disruptions to the base of the food chain would have starved many species and critically disrupted ecosystems. In the marine environment, the effects were just as severe. The combination of reduced sunlight and changes in ocean chemistry would have led to widespread die-offs of marine life, including plankton, which are crucial for the marine food web. The extinction of many marine reptiles and the examples of significant losses in ammonites and bivalves highlight how drastically the oceans were affected. Following the extinction event, the immediate aftermath presented a world stripped of biodiversity. Ecosystems faced drastic restructuring, and many niches that had been filled by various dinosaur species and other organisms were now vacant. The resulting environmental conditions paved the way for the rise of mammals and birds, but this transition took time as life slowly began to recover from the devastation. The extinction event fundamentally reshaped life on Earth, setting the stage for the evolution of new species in the subsequent Paleogene period. But the disruption at that moment was immediate and catastrophic for many existing forms of life. Fossils form through a complex process that typically requires specific conditions to occur. The journey of a fossil begins when an organism dies and its remains become buried quickly by sediment. This rapid burial is crucial because it helps protect the remains from decay and scavengers. Over time, layers of sediment accumulate on top of the remains, creating pressure that contributes to the fossilization process. One of the key processes involved in fossilization is called permineralization. During this process, groundwater carrying dissolved minerals infiltrates the buried remains. The minerals gradually fill the empty spaces within the bones or shells, ultimately hardening and preserving the structure as sedimentary rock forms around it. This is why many fossils are often found in sedimentary rock layers. Another important factor for fossilization is the environment in which the remains are buried. Ideal conditions often include low oxygen levels, which slow down decomposition. Environments like river deltas, lake bottoms, or ocean floors offer such conditions. Additionally, it is beneficial for remains to be buried in fine sediments, such as mud or silt, which can help preserve delicate structures. Conversely, harsh environments with frequent disturbance or high levels of erosion can hinder fossilization due to the exposure of remains to air and scavengers. Not all remains become fossils, and many factors influence whether or not fossilization occurs. For example, soft-bodied organisms are far less likely to fossilize than those with hard parts, such as bones, teeth, or shells. Additionally, the chemical composition of the remains and environmental factors play vital roles in this process. Over millions of years, fossils can emerge as a window into the past, taking us back to a time when those organisms roamed the earth and providing invaluable information about their biology and the environments they inhabited. Dinosaur fossils come in several types, each providing unique insights into these ancient creatures and their environments. The most well-known type is body fossils, which include the remains of actual dinosaur bones, teeth, and sometimes even complete skeletons. These fossils allow paleontologists to reconstruct the size, shape, and structure of dinosaurs, helping to understand their biology, locomotion, and evolutionary relationships. By examining the morphology of bones, scientists can identify different species and infer details about their lifestyles, such as whether they were herbivores or carnivores. Another significant type of fossil is trackways or trace fossils, which capture the foot impressions left behind by dinosaurs as they walked, ran, or interacted with their environment. These footprints provide invaluable information about dinosaur behavior, locomotion, and group dynamics. By studying the size and spacing of tracks, paleontologists can determine the speed at which a dinosaur moved and whether it traveled alone or in groups. These trace fossils reveal not just individual behaviors, but also insights into the ecological settings where these dinosaurs lived. Fossils of eggs and nests also contribute to our understanding of dinosaurs. Fossilized eggs can reveal information about reproductive behaviors, nesting strategies, and development of young dinosaurs. By studying the size, shape, and eggshell structure, scientists can identify specific dinosaur species and assess parental care behaviors. The discovery of nests indicates social behaviors among certain dinosaur species, suggesting they might have exhibited communal nesting, similar to some modern bird species. Additionally, fossilized skin impressions, feathers, and even remnants of soft tissues have been discovered in some specimens. These fossils provide critical information about the integumentary systems of dinosaurs, including insights into coloration, insulation, and behavioral adaptations. The presence of feathers, for instance, informs us about the evolutionary link between birds and dinosaurs, while skin impressions can reveal patterns, textures, and potential camouflage adaptations. The diverse types of dinosaur fossils, body fossils, trace fossils, eggs, nests, and soft tissue remnants, each offer unique perspectives on the life, behavior, and ecology of dinosaurs. By combining insights from these various fossil types, paleontologists can paint a more comprehensive picture of how dinosaurs lived, interacted, and evolved in their environments millions of years ago. Paleontologists employ several methods to determine the age of dinosaur fossils, utilizing both relative dating and absolute dating techniques. One of the primary tools for determining the relative age of fossils is biostratigraphy, which involves examining the layers of sedimentary rock in which the fossils are found. By studying the sequence of rock layers, known as strata, paleontologists can establish a chronological order. Fossils of different species are associated with specific geological periods, so finding a particular fossil can help date the rock layer in which it is embedded. By identifying the fossils present and comparing them to well-documented sequences from other locations, scientists can infer the relative ages of the fossils. In addition to biostratigraphy, paleontologists use radiometric dating to determine the absolute age of rocks and fossils. This method relies on the natural radioactive decay of elements within the minerals of the rocks. For instance, uranium lead dating or potassium argon dating can be applied to volcanic layers above or below the fossil-containing strata. By measuring the amount of decay that has occurred in the radioactive isotopes, scientists can calculate how long it has been since the rock was formed, providing an age range for the associated fossils. Another technique involves paleomagnetic dating, which examines the orientation of magnetic minerals in rocks. Earth's magnetic field has reversed many times throughout its history, creating a record of magnetic polarity shifts. By comparing the magnetic signatures of sedimentary layers with established timelines of magnetic reversals, paleontologists can estimate the ages of the rocks and the fossils within them. Lastly, advancements in technology, such as isotopic analysis, can further refine age estimates by examining the chemical composition of the fossils themselves. Certain isotopes can provide insights into past environmental conditions and help correlate fossil ages with known geological processes. Through the combination of these methods, paleontologists can build a robust timeline of dinosaur evolution, understand the timelines of extinction events, and place their findings in the broader context of Earth's history. Each dating technique complements the others, enhancing the accuracy of age estimations and helping scientists unravel the complexities of the past. Modern dinosaur fossil excavation and analysis employ a variety of advanced technologies that enhance the effectiveness and precision of paleontological research. One significant technology is ground-penetrating radar, which allows scientists to visualize subsurface structures without extensive digging. By sending radar pulses into the ground and interpreting the reflections, researchers can identify where fossils or fossil-bearing sediments are located, enabling targeted excavation efforts and minimizing damage to the surrounding environment. In the field, paleontologists often use portable X-ray fluorescent spectrometry to analyze the elemental composition of fossilized remains and surrounding sediments. This non-destructive technique helps identify the mineral content and can reveal essential information about the conditions under which the fossils were formed, such as the type of sediment and the pH of the environment. Such data provide context for understanding the diagenesis and preservation quality of the fossils. Three-dimensional modeling and digital imaging technologies have also revolutionized the way fossils are documented and analyzed. Methods such as laser scanning and photogrammetry create detailed 3D models of fossils, allowing scientists to study the morphology of specimens without physical handling. These digital representations enable comparative analysis, detailed measurements, and even virtual reconstructions, contributing to a deeper understanding of dinosaur anatomy and physiology. Furthermore, advanced imaging techniques, such as computed tomography, CT, scans, allow researchers to examine the internal structure of fossils in non-invasive ways. This technology is particularly beneficial for studying delicate or partially preserved specimens, revealing hidden features such as bone microstructure, potential soft tissue, and pathological evidence that may not be visible externally. Genomic technologies are also becoming increasingly important in paleontology. Although extracting DNA from ancient fossils poses significant challenges due to degradation over time, advancements in ancient DNA techniques and chemical analysis provide insights into the evolutionary relationships and possible traits of extinct species. These approaches can help clarify the connections between dinosaurs and their modern bird relatives. Collectively, these technologies significantly enhance the capabilities of paleontologists during both excavation and analysis, allowing for more precise, efficient, and comprehensive studies of dinosaur fossils. They not only increase the accuracy of findings, but also enable scientists to ask new questions and pursue innovative research avenues, further expanding our understanding of dinosaurs and their environments. Our understanding of dinosaurs has undergone profound transformations, especially in recent decades, primarily due to groundbreaking fossil discoveries. Earlier, dinosaurs were often portrayed as massive, lumbering creatures, based largely on incomplete skeletons and assumptions made from those limited finds. However, new and more complete fossils have emerged, allowing paleontologists to reconstruct not only the physical characteristics of these animals, but also their behaviors and habitats. For example, discoveries of feathered fossils from sites in China have revolutionized our perception of the theropod lineage, the group that includes modern birds. These fossils reveal that many dinosaurs were covered in feathers, suggesting that feathers could have originally served functions beyond flight, such as insulation or display. This finding supports the idea that birds are, in fact, descendants of a specific group of theropod dinosaurs, showcasing an evolutionary relationship that was once considered unlikely. Moreover, advanced imaging technologies, like laser scanning and three-dimensional modeling, have allowed scientists to study fossilized bones and structures in unprecedented detail. These technologies enable the analysis of growth patterns and biomechanics, providing insights into how these animals moved, how they cared for their young, and even how social structures might have formed among different species. The way we visualize dinosaur locomotion, for instance, has shifted dramatically, with some species now believed to have been agile and fast, rather than slow and sluggish. Finally, the discovery of dinosaur nests in fossilized tracks has contributed to our understanding of their behavior, indicating that some dinosaurs were capable of complex social interactions and parenting. As new fossils continue to be unearthed, our comprehension of these ancient creatures, including their diversity, behavior, and evolution, is constantly evolving, revealing a dynamic history that continues to captivate scientists and the public alike. Each new find adds depth to the rich tapestry of dinosaur life, reminding us that the past is far more complex than we could have ever imagined. The discovery of dinosaurs has significantly altered our perspective on Earth's history, particularly regarding the length and complexity of life on our planet. Previously, the understanding of geological time and the timeline of life on Earth was limited and often filled with misconceptions. The realization that dinosaurs roamed the Earth millions of years ago, during the Mesozoic era, which spanned over 180 million years, illustrated a much broader and dynamic picture of biological evolution. Dinosaurs served as a key connection in understanding major events in Earth's geological timeline. Fossil evidence has provided critical insights into the dramatic changes the planet underwent, such as shifts in climate, biodiversity, and the impact of catastrophic events. The mass extinction that marked the end of the Cretaceous period, for instance, led scientists to investigate its causes, unveiling the relationship between external factors such as asteroid impacts and volcanic activity, and their significant influence on biological and geological evolution. These ancient reptiles also act as indicators of environmental conditions throughout history. The study of dinosaur fossils has revealed information about ecosystems, including the types of flora and fauna that existed alongside them and how these systems interacted. This knowledge has reshaped our understanding of paleoecology and the planet's past climates, illustrating a complex interplay between life and its environments over geological timescales. Additionally, the appreciation of dinosaurs has fostered a broader interest in evolution and the history of life on Earth, encouraging interdisciplinary research that combines geology, paleontology, and biology. Discoveries of dinosaur fossils have opened doors to understanding more recent extinction events and ongoing ecological changes, reinforcing the notion that life on Earth is continuously evolving. Your view of the past becomes richer when you consider the vast timeline over which dinosaurs thrived, demonstrating that Earth's history is one of resilience, adaptation, and transformation. The study of dinosaurs offers profound insights into the processes of evolution and adaptation, showcasing how life responds to changing environments over millions of years. One of the most striking lessons from dinosaur research is the concept of evolutionary lineage, highlighting how species can diverge from common ancestors to adapt to specific ecological niches. For instance, the theropod group, which includes famous dinosaurs like Tyrannosaurus rex, evolved into various forms and eventually gave rise to modern birds. This evolutionary transition illustrates the dynamic nature of species and the role of adaptation in survival. Fossil evidence allows scientists to explore how different dinosaur species adapted to their environments. The diversity in body size, shape, and even behavioral characteristics among dinosaurs points to a wide range of adaptations to various habitats and ecological roles. For example, the long neck of Brachiosaurus enabled it to reach high vegetation, while the formidable teeth of carnivorous dinosaurs like Allosaurus indicate specialization in hunting. These adaptations were critical for survival and competition for resources within their ecosystems. Moreover, the study of dinosaurs includes examining how environmental changes, such as shifts in climate or habitat destruction, can impact evolution. The end Cretaceous mass extinction event is a powerful example, demonstrating how sudden changes can lead to widespread extinction, but also pave the way for new evolutionary paths. The survival of some small theropods in this tumultuous time eventually set the stage for the diverse avian lineage we see today. This scenario emphasizes the idea that evolution is not linear. Rather, it is influenced by a multitude of factors, including chance events and environmental pressures. Finally, the insights gained from dinosaur studies inform our understanding of modern species and the evolutionary processes that shape life today. By examining the changes dinosaurs underwent in response to their environments, scientists can draw parallels to contemporary issues such as climate change and habitat loss. The lessons of adaptation and resilience demonstrated by dinosaurs remind us of the importance of biodiversity and the potential consequences of environmental shifts, both past and present. Dinosaurs have made an indelible mark on popular culture and entertainment, captivating the imagination of people around the globe. One of the most notable influences is their portrayal in films, starting from early representations like the silent film The Lost World. In 1925, to the groundbreaking Jurassic Park, released in 1993, this film, which combined state-of-the-art special effects with a thrilling narrative, redefined the depiction of dinosaurs in cinema and sparked a renewed public interest in paleontology that persists to this day. Television shows and documentaries have also played a significant role in shaping public perceptions of dinosaurs. Programs such as Walking with Dinosaurs provided audiences with immersive experiences, blending scientific facts with engaging storytelling. These productions have not only educated viewers about dinosaur behaviors, habitats, and extinction, but have also brought dinosaurs to life in a way that feels both realistic and exciting, often inspiring a new generation of scientists and enthusiasts. The influence of dinosaurs extends beyond the screen, permeating literature, toys, and even theme parks. Dinosaurs have become popular characters in children's books, sparking curiosity and wonder. Toy companies have capitalized on this fascination, producing a myriad of dinosaur-themed products that can be found in playrooms worldwide. Theme parks, like Universal Studios, feature dinosaur attractions that allow visitors to experience the thrill of encountering these ancient creatures, further solidifying their status as cultural icons. Moreover, dinosaurs serve as a bridge between science and creativity, encouraging discussions around evolution, extinction, and the natural world. Their allure in popular culture often involves blending facts with imaginative concepts, fostering an environment where education and entertainment intersect. This unique position ensures that the legacy of dinosaurs continues to influence art, literature, and media, highlighting an enduring fascination with these magnificent creatures and their place in Earth's history. The closest living relatives of dinosaurs are birds, which are considered the direct descendants of certain theropod dinosaurs. This connection is supported by an extensive body of fossil evidence, as well as genetic studies that reveal significant similarities between modern birds and their dinosaur ancestors. Many characteristics found in birds, such as feathers, hollow bones, and specific skeletal structures, can be traced back to their dinosaur lineage, particularly to small theropods like Velociraptor. The discovery of feathered dinosaur fossils has solidified the link between birds and theropods, demonstrating that feathers were not solely a means for flight, but also served for insulation and display among various species. This has shifted the perception of dinosaurs from merely scaly, reptilian monsters to a dynamic group of creatures with diverse adaptations, much like the birds we see today. Interestingly, reptiles, such as alligators and crocodiles, also share a common ancestry with dinosaurs, as they belong to the group called archosaurs. This group includes both dinosaurs and modern crocodilians, showcasing a distant but significant evolutionary connection. While these animals are not direct descendants of dinosaurs, their lineage diverged from a common ancestor millions of years ago, emphasizing the broader relationship among these vertebrates. Overall, birds represent the most immediate and direct lineage, embodying the evolutionary legacy of dinosaurs. By observing and studying avian species, scientists can gain valuable insights into the behaviors, adaptations, and lifestyle of their ancient relatives. The survival of birds serves as a reminder of the resilience of life and highlights the long-lasting impact of dinosaurs on the evolution of species that inhabit our world today. Ongoing dinosaur research provides valuable insights that can enhance our understanding of current environmental challenges, particularly those related to climate change, extinction events, and biodiversity. By studying the fossil record, scientists gain critical knowledge of how prehistoric ecosystems responded to shifts in climate and habitat during Earth's history. Events like the mass extinction at the end of the Cretaceous period reveal the consequences of rapid environmental change on the planet's biodiversity, underscoring the importance of resilience and adaptation in the face of cataclysmic shifts. These ancient episodes serve as case studies for contemporary issues. Understanding how different species of dinosaurs adapted to their environments or failed to do so can inform our strategies for addressing present-day ecological crises. For instance, the adaptation strategies of some dinosaurs, such as dietary flexibility or changes in reproductive behavior, might provide clues for modern species struggling to survive in rapidly changing climates. This helps conservationists and ecologists develop targeted approaches to preserve endangered species facing habitat destruction and climate instability. Moreover, research into the extinction events that affected dinosaur populations encourage a broader understanding of the delicate balance within ecosystems. The interplay between environmental conditions and the survival of various species highlights the interconnectedness of life forms on Earth. Such understanding emphasizes the need for sophisticated models that predict how current species might respond to ongoing environmental pressures, whether from habitat loss, pollution, or climate fluctuations. Ultimately, studying dinosaurs highlights the importance of biodiversity, reminding us that the loss of any species can disrupt entire ecosystems. Insights gained from their history reveal that resilience and adaptability are essential, not only for survival in the ancient world, but also for ensuring the health and sustainability of our planet today. By learning from the past, we can better navigate the challenges we face in the present, fostering a more harmonious relationship with the natural world.